Namaste, dear viewers. I'm Dr. Sunita Goyal, working as an associate professor in the Department of Applied Sciences and Humanities at ABES Engineering College. Today, we'll discuss about NMR spectroscopy. This topic will be taken in two parts. In part 1, we'll discuss about the theoretical concept of NMR spectroscopy. And in part 2, we'll take its details and applications of this on certain or different types of molecules. So, what is NMR spectroscopy? Till now, we might have learned about the term spectroscopy. The spectroscopy is the study of interaction between the electromagnetic radiation with matter. Here, we are particularly concerned with our molecules for which structures, the chemical structures are to be determined. So, in the nuclear magnetic resonance spectroscopy, which is the full form of NMR, we study the molecules by recording the interaction of electromagnetic radiations which are from radio wave region with the nuclei of molecules which are placed in certain strong magnetic fields. Now, what is the principle of this spectroscopy? We know that electrons have the spinning property. They have spin states plus half, minus half. Just like electrons, nuclei also of some atoms have spinning property. What is the criteria of this spinning property for a proton is there? That is, these atoms must have either odd number of atomic number or odd atomic mass or both. For them, the nuclear spin quantum number I, it must be greater than 0. That means it cannot be 0 for them. Such nuclei or such atoms which are having nuclear spin quantum number I greater than 0, they are NMR active, or they will respond to this type of spectroscopy. Otherwise, they are inactive. So, the examples of NMR active molecules are 1H, 13C, 15N, 13F, 31P, etc. And if we want to take the NMR spectrum of C12, means carbon 12, or oxygen 16 isotopes, that will not be possible because their atomic masses are even and their atomic numbers are also even. So any of them or both of them, either the atomic number or the atomic mass should be odd. And here we know that most of the organic compounds contain hydrogens. So by knowing the hydrogens, we can know about the framework of that organic molecule. So we are particularly concerned here about the hydrogen atom. And we can say this hydrogen atom as proton because the atom of hydrogen contains the nucleus, and this nucleus contains only proton, not the neutrons. Therefore, we can say a hydrogen as atom, a proton, and we can say this 1H NMR as PMR, that means proton magnetic resonance spectroscopy, which is a useful way to study the whole structure of the molecule. Now, the atomic nuclei which are spinning, they are actually the charged particles because they are containing protons, which are the charged particles, which are positively charged. So a spinning charged particle generally creates an electric field and which is having a magnetic field component. Therefore, a magnetic field is there around a spinning charged particle, the proton or the nucleus of hydrogen atom. Therefore, these nuclei behave like tiny bar magnets as they are creating the magnetic field of their own. And when they are kept in an external magnetic field or applied magnetic field, they respond to this field. Here we can see in the picture, there is a spinning proton. It is creating a certain magnetic field which is around the magnet, which is around this atom, and it is having a certain direction. When these protons are present in when these protons are not present in any external applied magnetic field, their nuclear spins are random and the spins are also in random directions. So here we can see that there is no external magnetic field and the spins of their nuclei is also random. So they are randomly oriented. And when we keep these nuclei in an external magnetic field, their spins align themselves either with the field or against this field. So we can see here in the magnetic field, suppose this is the direction of the external magnetic field, some of the nuclei which were without the external magnetic field randomly oriented now have oriented themselves either in the direction of the field or in the opposite direction. Just like this, here this is in the direction of the magnetic field and it is opposite to the direction of the external magnetic field. Thus, the number of orientations or the spin states for hydrogen is 2. That comes out from the formula 2I plus 1, where I is the nuclear spin quantum number. For 1H hydrogen, the value of I is half or half integer. When we keep it here in the formula 2I plus 1, it comes out to be 2. Therefore, there will be 2 states, or when they are kept in an external magnetic field, the splitting of the protons, the splitting of these energy states will be there. Now they will not be degenerated. There are 2 energy states for a proton, a lower energy state with the nucleus aligned in the same direction as the direction of the external magnetic field, and the higher energy state in which the nucleus aligned against the external magnetic field. We can see here in the diagram that I is having value 0. This is the field strength and this is the direction of the external magnetic field. We are seeing the energy is increasing from bottom to top, and this state is now, it is the state when there is no energy difference. Now the external, after applying the external magnetic field, there will be the splitting between the state, between alpha, between low energy state and high energy state. Though low energy alignment, in the low energy alignment, we can see the nuclear spin states are in the same direction of the external magnetic field. And in the higher energy state, there is the opposite direction of the spins against the external magnetic field. This is the high energy alignment while it is the low energy alignment. And the energy difference between the two is delta E. We also can see here that when this nuclei, which is present in a sample tube here, when it is kept in the 2 pole pieces of the magnet, it orient themselves either in the low energy state or in the higher energy state. So these are the 2 pole pieces. This is north, and on the right side, it is south shown here in the diagram. When the south of the magnetic field of the nuclear spin is towards north pole of the external magnetic field and not toward the south of the external magnetic field, it is the low energy state. We can say it alpha spin state or calculate it as plus half. And when some energy is supplied to this spinning nucleus, it will attain a higher energy state or the beta spin state, for which the value is minus half. Here, This is the repulsive state because both the poles of the spinning nucleus is the magnetic field of the spinning nucleus and the external magnetic field, north pole, both are in the same direction, and south of these are in the same direction. So this is the repulsion, and here it is the attractive state, or the attractive forces are there. So it is the state which is having lower energy, and this is the state which is having higher energy. There is the energy gap between the two, and this energy gap can be filled when radio waves from the radio wave region of the electromagnetic radiation is supplied. Now, when an external energy source H nu that matches this energy difference delta E, for which we were discussing in the last slide, between these states, between these two states is supplied, the energy is absorbed, causing the nucleus to spin flip from one orientation to another. This transition from one energy state to another is called flipping of nuclei or proton. This energy can be supplied by electromagnetic radiation from the radio wave region. Here we can see that this is the setup which is shown here, that this is the north and the south pole of the external magnetic field, and this is the sample tube in which sample is there. And in this sample, protons are there, spinning protons are there, which are creating their own magnetic fields in certain direction. So there will be the creation of some energy states, low energy state and high energy state, and the energy will be required between the two to get resonate. So here from this arrow, we are showing radio wave input, which will help to cover up from the lower energy state to the higher energy state. And radio wave output will be there. And here radio wave frequency receiver is kept, which will detect the signal, which will detect this absorption of energy and will amplify it. And this is this is the absorption of radiation is detected on a radio frequency receiver, which is a type of Wheatstone bridge arrangement, which goes out of balance when absorption of radiation occurs. And the resulting signal is amplified and recorded on a spectrum instantaneously on a chart paper. So we can see here NMR spectrum. And in this experiment, in this instrumentation, the frequency of the radio wave is kept constant while the field strength is varied gradually. The wavelength of radio waves used are 0.3 to 10 raised to the power 9 meters. So long radio waves are there, that means of very low energy. And the frequency absorbed for this wavelength is 60 to 600 megahertz. And in NMR spectroscopy, the frequency we know is kept constant and the magnitude of the applied magnetic field is varied till the absorption of the radiation by proton, or which we say flipping of proton or resonance occurs. For resonance condition, the radio frequency nu, it is equal to 2 mu h naught upon h, where mu is the nuclear magnetic moment, and its value is constant for a certain proton. And h is the Planck's constant. 2 is already constant, mu is constant for a certain nucleus, and h is constant. Now, what is h naught? This is the field strength. Therefore, nu, the radio frequency or the frequency, becomes proportional to the field strength. And generally, 14,092 Gauss of the field strength is given to a proton when it is not in the vicinity of any external environment or the chemical environment. The electromagnetic radiation of 60 megahertz is required to resonate this proton. So, what type of informations we will get by doing this NMR spectroscopy? There are 4 types of informations we can get through which we can determine the structure of our molecule. Number 1, number of signals. Number 2, position of signals. Number 3, splitting pattern. And number 4, relative areas under signals. These 4 types of informations tell us about the whole framework of our molecule structure. So number of signals tells us about how many different types of hydrogens are present in our molecule. Means there may be certain sets of protons, like there may be alcoholic proton in our molecule, there may be methylene protons, there may be methyl or alkyl protons. So what type of protons are there and how many types of protons are there in our molecule can be known by number of signals. Now the chemical shift we'll discuss in part 2, but the chemical shift which tells us which is known by the position of the signals on the on the spectrum, that will tell us about what type of hydrogen is that. Means whether it is alcoholic or it is methylene or it is alkylic proton. So what type of hydrogen is there, that will be known by the position of that signal on the spectrum. And then we can know about the neighboring protons, or in the neighborhood of that particular proton, what type of hydrogens are there. We can know it by studying the splitting pattern of the signals. And there will be different heights of the signals on the NMR spectrum. By calculating or by knowing the relative areas under the signals, we can know how many any type of protons are there. For example, if alcoholic proton OH is there, so its number is 1. So signal will be 1. And if there are in its vicinity 2 CH2 protons are there, it is 2 proton signal. So its height or the area under this signal will be double than this one, because it is 1 proton and these are 2 protons. So by knowing the relative area under these signals, we can know how many certain types of protons are there. So that's about in this video. These are certain references through which we can know more about this topic. Thank you.